looks pretty good. How much that's doing? All right, 12 questions solved. Doing all right. We're getting there. They're mostly easy though. Hey, how's it going? Looks like I'm live. I was going to do today's LeetCode challenge. Just checking out my stats here. Most of my problems at this point have been the LeetCode challenge. I just started doing LeetCode recently, so I was just kind of curious about that. So here we go, day 8, and we've started another week. And see if there's anything they say about it. All right, looks like nothing new. So middle of the linked list. Okay, that sounds interesting. Given a non-empty, singly linked list with a head node head, return a middle node of the linked list. If there are 2 middle nodes, return the second middle node. Okay, that's a cool problem. I've never done anything like that before. I'm guessing this is also probably easy. So the deal with the linked list is that each node points to the next node, so you don't know how many nodes there are, so how do you know when to stop in the middle? So in this case, we would go to 1, and if there's only one element, I guess it's the middle. If we go to 2, then we would choose the second node. If we go to 3, then it would be this guy. We go to 4, it would be this one. And when we go to 5, it would be this node. And that's done. And I think that's how I'm going to do the algorithm actually. Is like I'm just going to go ahead and keep that kind of middle-y node. And then whenever we go past, so basically I'll keep 2 pointers, if that makes sense. And so I'll keep one for my current node that I'm looking at and a second one for the middle node. And basically every time I move one, I'll check my indexes and see if I also need to move that middle node. That will give us a runtime of O of n. And I don't think we can do any better than that. We'll have to look at each element, otherwise we won't know how long the list is. And the space complexity will be constant. We'll only have those 2 pointers, and we might need to store some indexes, but either way those will be constant. So I don't believe you'll be able to find a better solution than that. Of course there's always room for micro optimizations, but I think overall this is going to be a good algorithm, and this is just a fun problem. Oh, we got an interesting note here that we won't ever get more than 100 nodes. Don't know that really changes anything about the answer, but it's kind of interesting, I suppose. So I'm going to pseudocode this out a little bit. So if I have a linked list with 5 nodes in it, what I want to do is have 2 pointers, one for my current, and we'll say that's equal to head, and then one for my middle node, which is also going to start head. All right, and then what we'll do is as we increment, we'll keep track of our we'll call it our current index. And I think that might be it that we need. So let's see here. So while current.next is not equal to null, what we'll do is current equals current.next and current index plus plus. I'm going to go ahead and store the middle index right now too. I don't know that we necessarily need that, but we can always ditch it a little later. So that looks pretty good to me. Okay, so current index. So if ceiling, math.ceiling, this is how I'll make sure that I get the bigger number in case it's an even number of nodes. The ceiling of current index divided by 2, if that's greater than middle index, then what we'll do is we'll say middle index plus plus, and we'll set middle equals middle dot next. Is there anything else we have to do besides returning the middle? What do we return? Return the list node, so we'll return middle. So much for pseudocoding. I guess I just coded it. So is there anything that I missed where you loop through the list? That takes care of that. Okay, we keep track of our current index so we could do the math on it, divide by 2, and see if we need to increment our middle index. If we do, we'll increment it, and we'll go ahead and set that middle node. So basically we keep the track of the middlemost node at any given time. I'm happy with the runtime. I'm happy with the space complexity. I'm just going to run through this example. And we'll do one that has an even number, just to kind of make sure that the algorithm is sound. What I just realized is kind of weird is I never look at the value, but it does say we return the whole node, so the value really doesn't matter, other than, I guess, making it easier to debug. Alright, so in this case, we've got current, middle, current index, and middle index. I probably should have done this before I coded, but I didn't. So this will be the value there, just for thinking about it. Current index is 0. Middle index is 0. Okay, so while current has next, current goes 2. All right. Current index goes 1. 1 divided by 2 is going to be 0.5, and that should go to the ceiling, which should go to 1, which I don't like. That is kind of weird. So the current index is 1. I wonder if I should start with the 1 based index. Would that change things? Current index divided by 2. You know, actually, I think that's correct in this instance, because we should increment. If we only got 2 items in the list, then we should get that second element. So that's fine that we set to middle index, and we'll keep going and see how the solution works. All right, next up is our current is 2. It has next, so we will go ahead and bump that up to 3. Middle value stays the same for now. Oh, we changed it earlier though, sorry about that. Our current index is now incremented to 2. So we say 2 divided by 2 is 1. So we don't need to change our middle index. We don't change our middle value. All right, that's good. Move up our current index. So now we're looking at 4. The current index is 3. 3 divided by 2 is 1.5. Ceiling is 2. So our middle index increases, which makes our middle now here. So what we're basically saying is that if this was our whole linked list, then 3 would be the item that we count as middle. So I think that's sufficient for kind of vetting the algorithm. I think this is going to work. Runtime great, space great. I don't think you can do any better on paper. Runtime error, math.ceiling is not a function. What is a function? Is math.floor function? Is it seal? I am not a fan of abbreviations. All right, getting off the soapbox, staying focused. All right, it's gonna work now. 90% chance. Okay. That's a weird way of showing the answer, but that looks good. I'm going to go ahead and just do some minor cleanup and submit. I think this is it. Drum roll. All right, yeah, there we go. So let's look at the details. Okay, so in terms of runtime, we are on the crappier side of things. That's interesting. Memory distribution, where we had constant distribution, we're very good there. I'm sure somebody figured out how to get rid of some variables there. And there's a solution. So I'm curious how people got so much faster. I wonder if it's faster to just skip the check and just always set it. I got this tip, I forget who I got this tip from, but you could just click on the bar to see what the solution looked like, which is super awesome. So this is what it looked like for the people that kind of solved it my way. Is we basically have 2 pointers. They needed a slow pointer and a fast pointer. And they skipped the indexes, which is really nice. Let's take a look at the super fast end and see what the heck they did. So few people did this, I can't even click on it. There we go. Oh, they wait. So they loop through the whole list, count it, and then loop through the list again to return it. And that's faster? I don't understand that. I don't know why that would be any faster than looping through twice. Or, you know, once and a half, I guess. I mean, I guess it does involve less comparisons, but anyway, that's surprising. So definitely interesting. And you can see all the faster solutions do that. So it doesn't technically affect the runtime, but okay. That's how this stuff is. And here at the low end, yeah, definitely they only have 2 variables here that are returning. So a minor optimization there. So yeah, that was pretty cool. All right, I'm happy with that. I'm going to go ahead and run it over here just because I like to see the numbers. Okay, faster than 99.32% of JavaScript solutions. Heck yeah. Memory usage also was very low, and know we could trim that up. So I'm happy with that. I got my points for the day. Choo choo. All right, that's it. So I'm going to sign off for now. I will be back later. I'm planning to play with a little bit of Apache Beam. And today, gosh darn it, I'm actually going to file a new project that thing and do some coding with it. Come heck or high water. All right. Thanks for stopping by, and have a good one.